Hello. Yeah, can you hear me? Okay. So next we are going to see the octet rule. So what is octet rule? Write down first of all. Atoms forms, write down, atoms forms covalent bond covalent bond in order to attain noble gas configuration. Noble gas configuration, and for this each atom should have 8 electrons in the valence shell. In the valence shell. Okay. For example, HCl, CO2, O2, CH4. In fact, all hydrocarbon follows this rule. All hydrocarbon follows this rule. Yes, 8 electron in the valence cell. One second. Ah, in the valence shell. Okay. However, there are only few elements which follows this rule. Okay. Majority of the molecules does not follow this rule. Okay. That's why we have a lot of exception in this rule. Okay. So if you see this HCl, if I explain you this one, hydrogen never forms octet. It can form duplet. One or more than one also possible, covalent bond. Okay. So you see HCl, hydrogen and chlorine, right? So we have one electron here and one electron here. So for hydrogen, the duplet is complete. Chlorine, if you see, has 3 lone pairs on it, and hence bonding electron. If you count the number of electrons, only covalent. See, ionic is the transfer of electron. No, one atom has to lose the electron, other one has to gain the electron, right? So there we have exchange of electron, right? Hence, in that case, octet rule we don't consider because one atom has to lose, other one has to gain. Here we have sharing. So sharing takes place between the two atoms in order to gain octet for both atoms. So one atom, if it is losing, other one if it is gaining, right? So in that case, it is ionic bond, right? And octet rule we do not define for ionic bonds. Okay, it is not possible. So HCl you see, the octet of chlorine is complete, and hydrogen we have duplet of this. Okay, CO2, the another example, carbon O double bond C double bond O. For carbon, the number of electrons you count, it is 1, 2, 3, 4, 5, 6, 7, 8. Carbon has 8 electrons. Oxygen has 2 lone pairs on it. So the octet of oxygen is also complete. So for all these molecules, you see, all the elements will have its octet complete. Right? There are majority, like the most of the compounds, in fact, does not follow octet rule, but still they forms the compound, and those compounds are stable also. That's why all these compounds will study under exception of octet rule. Write down. Exception of octet rule. The first one, molecules, wait, write down like this, lesser than 8 electrons in the outer shell. Eight electrons in the outer shell means we have molecules in which the central atom has lesser than 8 electrons in the outer shell, but still the molecule is stable, right? It does not follow octet rule, but still the molecule forms. For example, you see, we have BF3, we have AlCl3, H2, etc. The BF3 molecule, if you see, the structure of BF3 is this. The structure of AlCl3 is also very much similar. And H2 we know already, H single bond H. All these molecules you see, the number of electrons for this boron in this compound, we have 6 electron, 2, 4, and 6. Here it is again 6 electron, 2, 4, and 6. And here it has 2 electron. So there are molecules in which the central atom has less than 8 electron, but still the molecule is stable. Right? So this is the exception of octet rule. Clear? I didn't get you, Kshitij. Balance as in? This molecule, it forms AlCl3. We use this as a catalyst in the reaction. But it is also possible that AlCl3 goes under dimerization and forms Al2Cl6. But yes, AlCl3 exists. It is stable. We use AlCl3 as a Lewis acid in organic reactions. That is why it is, yes, that is why it is an exception. But yes, dimerization is also possible and forms Al2Cl6. Okay. For which one? A structure we'll discuss, Shitish. We'll discuss VSEPR theory. There you will understand the structure. Okay, let's not go over there. Structure related things. We'll discuss that. Okay, this is the first exception of octet rule. The second one you write down, less than 8 electron. One more thing I forgot to write here. Less than 8 electron it's possible, and this kind of compound we call it as hypovalent compound. Less than 8 electrons, hypovalent molecule. And when we say less than 8 electrons, I'm talking about the central atom. We'll we count the number of electrons for central atom, aluminium, boron. Here we do not have, right? Central atom, I mean. That's why I'm calculating this 6 electron for aluminium here, for boron here, okay? Okay, second point. In case of, second, write down like this, more than 8 electrons, more than 8 electrons in outer shell. Eight electrons in outer shell. Okay. Write down, there are molecules. There are molecules which contains more than 8 electrons. There are molecules which contains more than 8 electrons, but still they are stable. Okay. For example, you see, example is SF6. We have PCl5, sulfate ion, SO4 2 minus, etc. SF6, if you look at the molecule and the structure, sulfur has 6 fluorine atom attached here. Okay, PCl5 has 5 chlorine. Okay, so all these molecules you see, the number of electrons this sulfur has, if you count, each bond has 2 electrons. There are 6 bonds. There are 12 electrons for the sulfur atom. For phosphorus, we have 8 electrons. So, 10 electrons. So we can see there are molecules which has more than 8 electron, but still they are stable. This kind of molecules which has more than 8 electron but stable, we call it as hypervalent molecule. Hypervalent molecule. Done. All of you understand this? How do we calculate the number of electrons here? How do we get 12 electrons or 10 electrons? Please tell me, all of you. Yes, 2 electrons in one bond. D shell, that's also right. Okay. Why these molecules shows more than 8 electrons? Because they have d orbitals available, right? Sulfur belongs to third period, phosphorus belongs to third period, and third period elements, we know they have vacant d orbital, hence they can expand their octet, and we call it as expanded octet. Okay, expanded octet. That's why you see mainly the P block of second period, those elements only shows or follows octet rule. Like boron also we have seen some exceptions in boron. Mainly we have carbon, nitrogen, oxygen, chlorine. These are the few elements which follows octet rule mainly. Other elements can easily expand their octets and can show expanded octet. Because of the availability of D shell, they can have more than 8 electrons easily. Okay. Yeah. Next, write down the third exception here we have. In case of odd number of electrons, in outer shell, these molecules we also call it as odd electron molecules. For example, we have NO, we have NO2, ClO2. All these molecules are odd electron molecules because they have odd number of electrons. You see this? Nitrogen has 7, oxygen has 8, 15 electrons, odd electrons. 7, oxygen has 8 into 2, 23 electrons, again odd electrons. 7 plus 8 into 2, 23 electrons, again odd number, sorry, is 17. 33 electrons, which is again odd number of electrons, right? So since we have odd number of electrons, it does not follow octet rule. Number 4, yes, outer shell has 7 only. I'm just calculating the total number of electrons. How do you find out the molecule is an odd electron molecules or not? So it is the total number of electrons I have taken. You see 7, 8, 7, 8 into 2 like that. Yes, that's right. Outer shell for chlorine has 7 electrons only. Okay. Yes, Pradhan, tell me. Okay. Now the fourth and the last exception we have is in case of transition elements compound. Means compounds of transition element. Okay. Okay. Now in this one, you see the example we have transition element compound. We call it as coordination compound. For example, K4Fe CN6. Right, this compound we call it as coordination compound, or we also call it as complex compound. There are many differences between the coordination compound and the simple compound like NaCl, MgCl2, etc. Those things we are not discussing now because we'll discuss this in grade 12. You have a chapter called coordination compounds only. They will discuss in detail of all these things. But here you see the metal here, that is iron, it takes electron from 6 cyanide. So obviously it has more than 8 electrons, 6 cyanide ion we have, and that's why it does not follow the octet rule. So in these 4 cases, the octet rule is violated. Okay, only second period element follows octet rule, right? In that also there are few elements like boron and all that does not follow octet rule. Okay, so this theory, these are the drawbacks in this particular theory of octet rule. That's why we require a new theory of bonding, right? And that is nothing but valence bond theory, MOT, molecular orbital theory, and other things which we'll discuss later. Before going into that, first we'll see the Lewis dot structure. This structure we draw based on octet rule only. Okay, Lewis dot structure. Write down the heading. There are rules which you need to follow here. Sorry. Write down this structure shows the bonding between the atoms of a molecule and the lone pair of electron. Okay, next write down rules for Lewis dot structure. Rules for Lewis dot structure. Okay, just we need to follow the rules in order to draw the Lewis dot structure. Okay, the first one, write down, count the number of valence electrons. The first step is to find out the number of valence electrons. Write down the first rule, count the number of valence electron. First of all, you write down the rules. I'll dictate it. Okay. Just a second. Hold on. Just a second, guys. Hold on. Wait. Rules. Okay. Fine. I'm not getting it. Otherwise, I would have shown you the rules. Not a problem. Okay. I wanted to show you the rules. It's not there. Anyways, Lewis dot structure. So first step, we'll find out the number of valence electron. Valence electron, right? We don't count the total electron. Valence electron only we count. Second point, add one electron for each negative charge and subtract one for each positive charge. Add one electron for each negative charge and subtract one for each positive charge. Add one electron for each negative charge and subtract one for each positive charge. Third point, choose the central atom. Choose the central atom. Generally, the least electronegative atom is the central atom. Generally, the least electronegative atom is the central atom. Okay. Then same third point, next line you write down, hydrogen can never be the central atom. Okay, all of you have written till here? Please tell me. Because this is important, we'll do the examples based on this. So I'll go slowly over here, right? So that all of you can write it down. Otherwise, you won't understand the example. Could you repeat the second point? Yes, second point is add one electron for each negative charge and subtract one for each positive charge. Okay. Now, fourth point you write down. Now, in third point you have written. In the third point, next line you write down, place the outer atom around the central atom. Place outer atom around the central atom and insert a pair of electron between the central atom and the outer atom. Yeah, I'll repeat. Place the outer atom around the central atom and insert a pair of electron between the outer atom and the central atom. Okay, this is the third point. All of you have written, please tell me. No, this is the third point only. In third point, I have given 3 points here, 3 different lines. Okay, now the next point, okay, or whatever number you have given, follow the same, okay? Let it be. Follow the same, but be alert, right? Don't mix this here and there. Okay, next point is, write down, place the remaining electron on the outer atom. Place the remaining electron on the outer atom as unshared electron Place the remaining electron on the outer atom as unshared electron in order to complete their octet. In order to complete their octet, starting from the most electronegative one. Okay, I'll repeat this one again. Place the remaining electron on the outer atom as unshared electron to complete their octet, starting with the most electronegative element. Next point. Place the remaining electron on the central atom. Place the remaining electron on the central atom remaining electron on the central atom. Next point you write down. Hydrogen should have maximum 2 electrons. More than 2 electrons for hydrogen is not possible. So hydrogen should have maximum 2 electrons. Beryllium should have 4. Beryllium should have 4. Boron and aluminium should have 6 electrons. Beryllium should have 4 and boron and aluminium should have 6 electrons. Done? Beryllium should have 4. Beryllium should have 4. Boron and aluminium should have 6 electrons. Done? Boron and aluminium. Done? Okay, these are the rules we have to follow in order to draw the Lewis dot structure. Main is this. Okay, now in this, there are certain few points that you have to take care of. Next, write down, and this point all of you write down carefully. Write down, if the central atom has more than 8 electrons, if the central atom has more than 8 electrons, then its atomic number should be more than 11. 2, 3 more points we have. If the central atom has more than 8 electrons, then its atomic number should be more than 11. Done? Now the next point is very important. Okay. Okay, write down. If central atom has if central atom has less than 7 electrons, central atom has less than 7 electrons, then move an unshared pair of electron, then move an unshared pair of electron from the outer atom to form a double or triple bond with the central atom. Done? Yeah, I'll repeat. If the central atom has less than 7 electrons, then move an unshared pair of electron, from the outer atom to form a double or triple bond with the central atom. Done? Okay. Next point, calculate the formal charge. Calculate the formal charge on each atom. Formal charge on each atom. So the formula for formal charge is V minus half of S minus U. S is the shared pair of electron. V is the number of valence electron. And U is the number of unshared electrons. With examples, you will get it. Okay. Okay, one more point to write down. If a molecule is hypervalent, okay, write down. If the molecule is hypervalent, then the charge on the central atom should be 0. If the molecule is hypervalent, then the charge on the central atom should be 0, or the charge on the ion. Okay, I'll repeat this point again. If the molecule is hypervalent, then the charge on the central atom should be 0, or the charge on the ion. Tell me, all of you have done? We'll start the examples then. Yes? Okay. With examples only you will understand the rules that you have written. Suppose the first molecule I am taking, that is carbon tetrachloride, CCl4. We need to draw the Lewis dot structure of this. Okay, Lewis dot structure of this. The first step is to calculate the number of valence electrons. So we'll calculate the number of valence electron. Valence electron means in the valence shell, how many electrons are there. For carbon, the number of valence electron is 4. And for chlorine, it is 7. But there are 4 chlorine atoms, so 7 into 4. So it is 32. 32 valence electrons we have. Next is, we'll find out the central atom. Identify the central atom. So least electronegative element is the central atom. Carbon should be the central atom. Around the central atom, we'll place the outer atom, which is chlorine here in this case. So we'll place this. Next is what? We need to distribute this 32 electrons in this among these atoms, carbon and chlorine. How we'll distribute that? We'll start from this. Means one pair of electron we insert between the central atom and the outer atom like this. Okay. Out of 32, 8 electrons we have used. Remaining is 24 electrons. That 24 electrons we start placing on the outer atoms in order to complete their octet. You see this chlorine, if you ignore this one, this chlorine has 2 electrons. This chlorine requires 6 more to complete its octet. We have 24 electrons. So out of 24 electrons, 6 electrons I'll place here. This chlorine octet is complete. For this also we'll do the same thing. We are left with 12 electron after this, right? Out of 12, 6 electron will place here. right? 6 electron will place here. We are left with 6 more electrons, and the last 6 electrons will place on the chlorine, and this is the distribution of electron. This is a very basic example I have done. Okay. Now, if you draw this, you see the octet of all the atoms are complete. The last step, when you do everything, the last step is to calculate the formal charge. Okay. Let's see how to calculate the formal charge. Formal charge actually we calculate on each atom, including the central atom and the outer atom. So bonding of all chlorine are same. The formal charge on carbon is what? Formula we use, number of valence electron 4 minus half of the shared electrons. 2, 4, 6, 8 electrons are being shared. 8 plus the number of unshared electron on this carbon. There is no unshared electron. Sorry, we have negative also in the last. There is no unshared electron. Unshared means any lone pair is present or not. That is 0. So this should be 0. The formal charge on carbon atom is 0. For chlorine, if you find out the formal charge, 7 is the valence electron. And for each chlorine, the bonding is same. Any one you can take. This is the unshared electron. Sorry, shared electron is 2. So half of 2 electrons are shared, minus we have 6 unshared electrons, unpaired electrons. This is also 0, right? Hence the formal charge on chlorine as well as carbon is 0. So this is the Lewis dot structure of CCl. Okay. If you want, you can place this circle in order to show the octet of the atom. Like this you can place. See the carbon, the octet is complete. You see this. Okay. For chlorine, the octet is complete. You see this. This chlorine also the octet is complete. This chlorine also the octet is complete, and this chlorine also the octet is complete. Okay. So all the atom has complete octet with 0 formal charge. So this is the best possible arrangement of atoms. Remember, if you have placed everything and formal charge, if you do not calculate, if you do not put, if any, then the entire thing will be wrong. Without formal charge, nothing is correct. Did you understand this? Right? Let's take another example. CO2. Tell me the valence electron for carbon dioxide. The number of valence electron and which one is the central atom here? How many valence electrons are there? Okay, Arya, not a problem. But if you look at these examples, you will get it. Okay, what is the Lewis dot structure? Tell me the number of valence electron, guys. What is the number of valence electron? Parvati, Auro, Pranav, 16 you are getting. Okay, number of valence electron for carbon it is 4. For oxygen it is 6 into 2. So we have 16 electrons. Central atom. What is the central atom here? No, not Pranav. It's in other batch. We have carbon, right? So carbon is the central atom, and oxygen will place on the other side of carbon. Okay, Then this 16 electron we have to distribute. So I'll place one electron here, one pair of electron here, another pair will place here. Now we'll distribute the electron on the outer atom starting with the most electronegative one, because we have oxygen only, so we'll place anywhere. But suppose we have two different atoms here, oxygen and other atoms, then the one which is more electronegative will give the electron to that particular atom first. So here I have given you the rules, Pradyum. Central atom is generally the least electronegative one. And if you have two oxygen and one carbon, obviously it's common sense that oxygen cannot be the central atom. Symmetry, if you see. Right? So carbon is the central atom, least electronegative one. Okay. So we are left with 12 electrons. So we'll place 6 electrons on this oxygen so that the octet of oxygen is complete. Then I want you to go through one point here, maybe the point number 9 or 10, in which it is written that, all of you, listen, if central atom has less than 7 electrons, could you see that point? 10th, 1 or 9th or 11th, you can check. If the central atom has less than 7 electrons, did you see that? What is that rule? If the central atom has less than 7 electrons, then move an unshared pair of electron from outer atom to form double or triple bond. Correct? So what we'll do, we'll move one electron here, right? You see this? Carbon has 4 electrons in this bonding state. So one pair will move here in order to make a double bond with carbon atom like this. You see, still the octet of carbon of oxygen is complete. Oxygen has no loss here. Whether you place this 2 electron here, the octet of oxygen is complete. If you place the 2 electron here, still the octet of oxygen is complete. So oxygen has no loss into this one. But the advantage is what? Carbon has had 4 electron, now it has 6 electron. Again, you shift this electron pair over here, and we are doing it according to the rule. Then you see oxygen is still, the octet of oxygen is complete, but carbon also has complete octet. So this is the distribution of electron, the perfect distribution of electron. The last one is what? No, it's not the bonding. We are trying to understand the distribution of electron. How do we draw the Lewis dotted structure? In Lewis dotted structure, we do not draw the line, single bond or double bond. We don't draw like this. We just put this dot. So there's no point of talking about here the coordinate bond or covalent bond or something like that, because we don't represent the bond. We just represent the electrons here. Okay. Now last step is what? To calculate the formal charge. The formal charge, if you count on oxygen, could you tell me the formal charge on oxygen? For oxygen, it would be 6 minus 4 electrons are there. So half of 4 minus 4 electrons are there. So 0 formal charge on oxygen. For carbon also, if you count, you'll get 0 formal charge on carbon. So this is the structure of CO2. See, you can draw other structures also, right? You can draw other structures. Like you can ask me, like I have done this. All of you see this? if you are asking first of all, if you are asking why to count formal charge, okay, you can also ask me, sir, why to distribute electron like this? We are calculating formal charge to write down the Lewis dot structure. That's the answer your question. But the thing is, there are many other distribution possible. It's not like only one kind of distribution is there. Okay, but with the distribution of electrons, the formal charge changes. Without the formal charge, the molecule is not stable and it is not correct structure. Not stable, we cannot say. Not correct structure. Like you see, I'll give you one example here only. I had done this. You did not ask me this question, but you could have asked me this question also. This was the arrangement we were talking about, right? Where we have and then I said what? That one electron, one pair of electron I'll remove from here and I'll place it here, right? And then what I said, one electron from this side will place it here. You can ask me, so why not you place this electron here only? Can we do this? Can we do this? Right? So point is, we can do this, but this structure is not right now. It's not right now. When you place the formal charge, we'll have a formal charge on this oxygen. If you find out, you'll get a negative formal charge here and a positive formal charge on this oxygen. Most probably, you can count, you'll get that. So with this formal charge, this structure is correct. If you do not draw the formal charge, your structure is wrong. First thing is that. Second thing, which one is the acceptable one? Acceptable one is the one in which the atoms has no formal charge. Means in this and this, if you compare, this is negative and this is positive. This is a more stable structure. That's why we draw this way. Did you get my point? Yes. Tell me, guys. Yes, I can show you one more thing here. Okay, let's discuss this way also. If you draw a bond here, this structure is nothing but this one: O double bond C double bond O, isn't it? This, yes. And this structure is nothing but O single bond C triple bond O with one lone pair, with three lone pair, one negative charge and one positive charge. Okay. Now, if you see this, this is a conjugated system. Pi sigma lone pair. If you draw the resonating structure for this one, then what you'll get? You'll get this one only. Yes or no? Could you connect this with resonance? Yes. So now you can answer your question itself. If you do not put the charge over here, will this structure be correct? No, it's not. Is it? Right? So the thing is that when you distribute the electron, the distribution of electron leads to some charge on the atom, correct? Without placing those charges, the structure is not correct. It's a different matter that which structure is more stable one, this one or this one. The more stable one only will draw, right? But we can draw this structure also. Obviously, this is a resonating structure for this one. So this is not wrong, but yes, it is not as stable as this one is. Is it clear? Tell me. Okay. Could you draw this one? We'll do many examples into this one because with example only you will understand this. XCF2 you try. XCF2. All of you. Let me know once you're done. Okay. So in this one, how many valence electron? 8 for xenon and 7 for fluorine. 22, right? Obviously, xenon is the central atom, the least electronegative one. Fluorine will place this side. Then one pair in between the atoms. We are left with 18 electrons. So 1, 2, 3, 4, 5, 6 octet is complete. 1, 2, 3, 4, 5, 6 octet is complete. How many electrons we are left with? 6 plus 6, 12, 12 plus 4, 16. We are left with 6 more electrons. So we have 3 lone pairs on xenon. This is the structure. Yes. Then if you calculate the formal charge, what is the formal charge on xenon? Xenon, the formal charge 8 minus half of 4 minus 6. So 0. There is no charge on xenon. Fluorine also we have 0 formal charge. Hence this is the structure we have, Lewis dot structure. Any doubt? Try this one. XeF4. Done? Yeah. So XeF4, how many valence electron, Parvati? Kshitij, how many valence electron? Is it 36? Yeah. 8 plus 7 into 4, 36. So central atom is obviously Xe. Then fluorine, 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 and fluorine. Okay. So we'll have 1, 2, 3, 4, 5, 6, 7, 8. Then 6 electron on each fluorine atom. That plus this is 32. 32 electrons we have used. So xenon will have 2 lone pairs on it. Is it 2 lone pairs on xenon? Right? Formal charge on fluorine is 0. Xenon, it's also 0. If there is any formal charge, you have to place it. like -1 +1 on the atom. You have to place it, right? You cannot count like this and leave. Okay, this is just I am doing it for you to understand how to calculate the formal charge. But if it is any formal charge there, like -1, -2, +1, then you have to place here on the atom. Okay, understood this one? Fine, we'll do some more examples into this, okay, next class, and then we'll continue with the other theory of bonding. Okay, some more example is required. Assignment I have given you already. Module questions you need to solve, redox and mole concept 2. Okay. Yeah. Thank you so much, guys. We'll see you in the next class. Take care.